About number theory. Number theory is mostly concerned with natural numbers, which we were talking about in set theory. Those are the counting numbers. So in general, we're talking about positive whole numbers when we talk about number theory. Now, that's not all number theory covers, but that's what most number theory covers, is stuff to deal with those numbers. We already talked about the set of natural numbers and how you can define it visually in set theory. This is the roster method, but we just have the bold N is equal to the set 1, 2, 3, 4, 5, 6, forever. Just keep going up by 1. And then if you multiply natural numbers together, you get factors of the product. So, for example, if we take 24, 2 and 12 are two natural numbers that make up 24. So 2 and 12 are factors of 24. So are 3 and 8, 4 and 6. Some numbers have very few factors. So for example, the number 6 only has the factors of 1 and 6, which, that makes up 6, and then 2 and 3. So 4 factors. Some numbers only have 2 factors, like the number 3 only has 2 factors, 1 and 3. 24 has lots of factors. You have 1 and 24, 2 and 12, 3 and 8, 6 and 4. So, and it doesn't matter the size of the number. Some very large numbers may only have 2 or 4 factors, and some very small numbers like 24 can have a lot. All right, we talked about divisibility. Divisibility is the ability to divide evenly. So if you have two numbers, A and B, A is divisible by B if you divide it and there's no remainder. It divides evenly and gives you a 0 as a remainder. Okay. Divisors divide in to the numbers. So if you think about when we talked about long division back in the day, and you had things like this, 27 will divide evenly by 3, so 27 is divisible by 3, and 3 is called the divisor. And if something is divisible evenly, you can symbolize it this way. So we could say 3/27. Now that does look like March 27th maybe, but that's not what it is. This is saying that 3 evenly goes into 27. 4 evenly goes into 24. We talked about this is the divisor. This is called the dividend. Anybody remember what the answer is called? Quotient, yeah. So when we do that, 3 goes into 27 9 times. 9 is our quotient. Brings me to an interesting thing. 27 is divisible by 3. It's also divisible by 9. So once you know one, you can find the other, or at least one of the others. There's multiple. Oops. There's multiple ones. Here's how you can tell if numbers divide evenly by these numbers here. Now you'll notice that I did not put 7 on the list. That is not because 7 doesn't have a rule. 7 has a rule. But the rule to figure out if a number will divide evenly by 7 is actually more complicated than just dividing by 7 and seeing if it works. So I'm not teaching it because it's silly. The divisibility rules are meant to make things easier, not harder, right? So to tell if a number divides evenly by 2, look at the last number. If the last number in the number is even, the whole number divides by 2. So 0, 2, 4, 6, or 8 is your last digit, and that's for any size number. Okay, so that one's fairly straightforward. Number 3 is a little bit trickier. For number 3, you add up the digits of the numbers. If the sum of the digits will divide by 3, then the whole number will divide by 3. So I mentioned 111 earlier. 1 plus 1 plus 1 equals 3. That's how I knew 111 would divide by 3. If I had a number, say for example, 279, and I want to know, will that divide by 3? All right, let's make it bigger. I want to know if that'll divide by 3. If I add these together, they're 2 plus 7 plus 9 plus 8 plus 1. I get 27. 27 will divide by 3. So 27,981 would also divide by 3. So once you know this trick, any number, if somebody asks you, will this divide by 3, you just add the digits up really quickly. And if the answer you get divides by 3, then the whole thing will. And if it's a long number and you get some number that you don't know if it'll divide by 3 or not, add those digits up and keep adding the digits until you get a number small enough to know, oh, hey, yeah, that divides by 3. Or it doesn't. In some cases, maybe you get like 29. That won't. For 4, 4, 2, 4, and 8 are kind of related. To figure out 2, you look at the last digit. To figure out 4, you look at the last 2 digits. So if the last 2 digits of the number divide by 4, then the whole number divides by 4. So for example, if I had some number 356,924, and I want to know, is that going to divide by 4? All I need to do is look right here. 24 divides by 4, so this whole thing will divide evenly by 4. 5, most of you seem to already know that one. If it ends in 5 or 0, then the whole thing divides by 5. 6 is a combination of 2 and 3. So the rule for 6 is to combine the rules for 2 and 3. So if it's even, so it ends in 0, 2, 4, 6, or 8, and you add it up and it divides by 3, it'll divide by 6. So if it divides by 2 and 3, it divides by 6. Eight extends on the 2 and 4. 2 is 1 digit, 4 is 2 digits. So for 8, you look at the last 3 digits. So you can take a long number, just look at the last 3 digits and divide those by 8 quickly. And if that divided by 8, then you know the whole thing will divide by 8. 9 is similar to 3. You add up all the digits, and if the sum of all the digits will divide by 9, then the whole number will divide by 9. So this number up here that I used, 27981, if I added those up, I got 27. 27 divides by 9, so 27,981 would also divide by 9. Yeah, but this last 2-digit thing doesn't work. Because if I rearranged this, let's say I did 28971. 71 doesn't divide by 9, but that number still will, because when I add those up, I'm still going to get 27. Okay. Does that make sense? And then 10. 10's the really hard one. The number has to end in 0. Very confusing. I'm kidding. We're going to be factoring. We're specifically concerned with prime factorization. 2 is prime, 3 is prime, and 5 are prime.
So
Mm-hmm. And yep, we're going to be doing that. So you want to know how to tell if numbers divide by the primes. So unfortunately, 7 would be our next prime. But again, the rule for 7 is harder or more complicated than just dividing by 7. So you check 2, you check 3, you check 5. If those don't work, you check 7. There's a rule for 11, but again, it's like 7, it's very complicated. Okay, prime number. Oops, wrong thing. Okay, prime numbers are natural numbers. Okay, so negatives are not prime. 0 is not prime. It's a natural number that's greater than 1. So 1 is also not prime. That has only 2 factors, itself and 1. So 2 factors only. And this is why number 1 is not prime. The number 1 only has 1 factor. Basically, you have 3 kinds of numbers. Well, 2 major kinds of numbers. You have prime and composite. Prime numbers only have 2 factors, 1 in themselves. Composite numbers have more than 1 factor. Always in sets of 2, though, so even numbers of factors. So you have prime and you have composite, and then you have numbers like 1. 1 is neither prime nor composite because it doesn't have only 2 factors and it doesn't have multiple factors. It has 1 factor, and so it's kind of like this weirdo that doesn't really fit in with the whole scenario. Okay. There are theories in math that are called fundamental theorems, and the reason they're fundamental is because kind of everything else builds on them. We have the fundamental theorem of arithmetic, we have the fundamental theorem of calculus. We're not going to do that one, don't worry. The fundamental theorem of arithmetic tells you that every composite number can be expressed as a product of prime numbers in one and only one way. Essentially, like people, each number is unique. So if I factor 2 different numbers, I'm not going to get the same prime factorization. And if I take one number and I start factoring it and I split it up differently each time, so the first time I divide by 10, the second time I divide by 2, another time I divide by 5, and I break it up all the way down to its primes, no matter how I started, I'll always end the same, with the same set of numbers. That's what that theory tells us. And one way that we find prime factorization is a factor tree. Bad name really because trees go up. These should be called factor roots because they go down. But we can also do them sideways. And then I'll show you another method that I don't actually know the name of. So first let's start with some divisibility. We're going to list down which numbers out of that list I just gave you, these numbers are divisible by. Yeah, 2 right off the bat because it ends in an even number. 4 because the last 2 digits divide by 4. Yeah, if I add these together, I get 7, 8, 10. So it does not divide by, doesn't divide by 3. We can check to see if it divides by 8. 8 goes into 31 3 times, 24. With 7 left over, 72. So 8 will go into 312. Other way I could have known that, 2 times 4 is 8. But just check it to make sure all the If it doesn't divide by 3, it won't divide by 9 or 6. Because 6 has to divide by both 2 and 3. Doesn't end in 5 or 0, so it can't divide by either 5 or 10. We'd have to try it. So 7 goes into 43 6 times. That's 42, which leaves 11. So 7 goes into 11 once, with 4 left over, which gives me 42. So 7 would work. We don't have to go any further than that for right now. Okay. 562,110. 2 works. 5 works. 10 works. Let's test for 3. Don't have to add the 0. I get 11, 12, 13, 14, 15. So it will also divide by 3. Yeah, it does divide by 2 and 3, so it'll divide by 6. 15 doesn't divide by 9, though, so it won't divide by 9. And then if you want, you can try 7. But we're just going to skip 7 for right now. 375. I get what when I add these together? 15, so it'll divide by 3. Anything else? 918. 2. Not 4. Yeah, because 18 won't divide by 4.
3. And 6.
When you added those up together, what'd you get? 9 plus 1 plus 8, you got 18, which will divide by 3, but it'll also divide by 9. 111. 3. 1,110.
2, 5, 1, 2, 3.
Well, 3 because the 111 divided by 3, and we just added a 0 to the end. So 5,
6.
10, and 6. Okay. Divides by 2. Does 54 divide by 4, though? No. 54 is 6 times 9. There's no 4 in there. We add the digits together. Okay, here's what I do. 9 makes a 9, that's divisible by 3, and 1 and 8 make a 9, which is also divisible by 3. 3 and 4 and 2 make a 9, which will divide by 3. And this makes a 9. So I have 1, 2, 3, 4 9s, essentially, which is 36. So this whole thing's going to add up to 36. I did it by groups of 9s.
Okay.
Or you can add it up the long way. Either way, you get 36, which will divide by 3 and 9. So we also get 6. Okay. If it didn't divide by 4, it's not going to divide by 8. Okay. Sort of the same thing. If it did not divide by 3, it's not going to divide by 6 or 9. So that's our list. Prime factorization of 700, and I'm going to use this to prove the fundamental theorem of arithmetic. We're going to start 700 out in 2 different ways and see if we come out with the same numbers. Yeah, we're going to do a factor tree both times, and then I'll show you how to do it another method. Okay, so how do we want to start it? What's 700 divided by?
Just start with
10 and 70, right? And 10 is, and 70 is, okay, now once you get to the end of the branches and you get your prime numbers, you can't go any further. I have a 2, a 5, another 2, another 5, and a 7. So if I write that out, and then I can also use exponents, 2 squared, 5 squared, oops, not 7 squared, just 7. Okay. Now, oops, let's break 70 up or 700 up a different way. Ones aren't very useful.
You could do 7.
I can do 5 times 140. You know how I knew that really fast in my head? Is 10 is 2 times 5, so I took the 5 out and then put the 2 over here. And we had done 7 times 10 before. I'm going to do 2 times 35 this time. And I get a 5, 2 2s, another 5, and a 7. Same thing. It doesn't matter how you start. There's no wrong way to start. As long as you divide properly, you'll get to the end the same way. Now, the other method that I can show you for prime factorization is kind of like upside down division. There's a name for the method, but I can't remember it because it's named after the lady that came up with it, and I don't remember her name. Okay, so it's like a factor tree, sort of.
Except just upside down.
It's upside down division. So 700 divides by 10, correct? And then, well, actually, let's not do that. Let's do primes on the side. 700 divides by 2. 2 is a prime number. And when I do 2 into 700, I get 350. 350 will divide by 5. Do you remember this? Okay, 5 goes into 35 7 times and into 0 no times. And then 70 will divide by 5. 5 goes into 7 once with 2 left over. So I get 14. And 14 will divide by 2 and it gives me 7.
Same thing.
Same thing. So if you don't like the trees, you can do upside down division and you get the same answer. You can do the trees if you don't like the trees going down because it takes up too much room on your paper. You can do them sideways. So it's a matter of preference. But no matter how I do this, I end up with 2 2s, 2 5s, and a 7. 700 will always give me 2 2s, 2 5s, and a 7. It's a list of primes. This is how you can find at least the primes up to 100 fairly quickly. The longest part is writing down 1 through 100. Okay? Now, 1 doesn't really count, so I'm going to go ahead and cross that one out. 1 is not prime. So 2 is our first prime number. So what I do is I circle 2. Now, anything that divides by 2 can't be prime. So I can get rid of every other even number on this list. Because none of them are prime. So my next number on the list is 3. 3 is prime. Every number that multiplies by 3, however, won't be prime. So you got 3, 6, 9, 12, 15, 18, 21. So I'm just going up by 3s, right? 24, 27, 30, 33, 36, 39, 41, 45, 48, 51, 54. See 3 more numbers over? You don't even have to count. You just say, okay, like, here's 3 more over, here's 3 more over. 60, 63, 66, 69, 71. No, not 71, sorry, 72. 72, 75, 78, 81, 84, 87, 90, 93, 96, and 99. I got rid of all the multiples of 3. Those numbers are not prime. The next prime number is 5. So I get rid of all the multiples of 5. But yeah, because we already took care of the zeros, right? 2. So my next prime number is 7. So I'm going to get rid of the multiples of 7. I have 7, I have 14. 21 was already taken care of with the 3. What's next? 28? 28 is 7 times 4, that's done. 7 times 5, 35, done. 7 times 6 is 42, done. 7 times 7 is 49. Take care of that. 7 times 8 is 56, done. 7 times 9 is 63, done. 70, done. 77. 7 times 12 is 84. If you don't know 7 times 13, that's okay. We could count there. So we could say the next numbers. So 1, 2, 3, 4, 5, 6, 7, 92, or 91. Gone. Add 7 to that. 98's already gone. Once you take out all of the multiples of up to 7, if you're only going up to 100, everything else is already taken care of. There are no more multiples of anything on this chart. Because if we go to the next prime, which is 11, we'd have 22, 33, 44, 55, 66, 77, 88, 99 are already gone. Same for 13. Because if I multiply, say 13 times 13, I'm already more than 100. So all of the primes are all the numbers that you haven't crossed off yet. They're crossed, and you find them. Did I miss any? Nope. There you go. All your primes up to 100. These are the numbers you need to check when you're factoring.
I think I missed it, but what makes it prime?
Prime can only divide by itself and 1. So nothing else will divide into it. So like if I look at, say, 13, nothing divides evenly into 13. That's prime. That's why we could cross out like all multiples of 2 or 5, because if they multiplied, if there are multiple of those numbers, then they can't be prime. So here you go, your list of prime numbers up to 100. 100, of course, not included on that list because it's not prime. So let's make some factor trees. Ow. 276 will divide by what? 2. Okay, let's start with that. You pick one and start with it. Okay, 2 goes into 2 one time, goes into 7 3 times with 1 left over, and then there goes into 16 8 times. I'm doing what's called short division, by the way. Has anybody ever showed you guys short division? Yeah. Anybody need to see short division? All right, if you guys decide you want to see short division, just let me know. Okay, 138 divisible by 4. Ends in an even number. 2. Yeah, if it ends in an even number, you can keep dividing by 2 until it's not even anymore, and then you go from there. That's how I approach these. I usually go, oh, it'll divide by 2, and then I just keep dividing by 2 until I can't divide by 2 anymore. Then I try 3 or 5. No, because 38 doesn't divide by 4. Now 276 would have. But 2 goes into 13 6 times with 1 left over. divide by 3. And now 23 is prime. So our prime factorization is 2 times 2 times 3 times 23.
So 2 to the second power times 3 times 23. Which gives us 236.
So either of these will work if you want to use the exponents or not. Exponents are nice so you don't have to write as much.
You don't have to solve it.
No, well, if I solve it, if I multiply that all back together, I'll get 276. Yeah. So you can do that though if you want to check yourself to make sure that you factored it correctly. What color you guys want to factor in next? Purple, okay. 3,216 will divide by 3. Yes, it'll divide by 3. And it'll divide by 6. Okay, 3 goes into 3 one time. It doesn't go into 2 at all. It goes into 21 7 times, and it goes into 6 twice. So this will divide by 2. Divide by 2 goes into 10 5 times. It goes into 7. Oh, 3 times. Sorry. That's 3 with 1 left over, which gives me 6. Okay, 536 will divide by
6.
Mm,
It's 36.
not the last 2 digits. Remember, it has to divide by 2 and 3. Which this will divide by 2, but if you add it up, you get 14. So it won't divide by 3. But we'll do 2. 2 goes into 5 twice with 1 left over. It goes into 13 6 times with 1 left over. It goes into 16 8 times. 2 goes into 268 134 times, which is also divisible by 2. 67 is prime. So we have 1 3, 1 2 3 4 2s.
If you pick the bigger number from the start, would it do less?
Yeah. No, you're going to be doing the same division. You'll just have different branches.
Right, but
That's what he's
long
saying.
division, if you pick the biggest number, it would.
Right, but then you have 2 more numbers. That number that you picked that was bigger, you have to divide. But it doesn't matter how you do it.
If you started with 67.
Yeah. So let's go with let's try it with 3 2 1 6. What do you want to divide it by first?
Start with 67.
Okay, 6 goes into 32 5 times, 21 3 times, and then 36.
You said 21 3 times.
Yeah, 18. 6 times 18. So I get 6 and 5 out of 36. 6, that one's easy. I'll do that one. You guys can do that one.
2 and
Not 6, because this won't divide by 3. 2, and actually,
it's the same thing.
yeah, does not matter how you break it up, you're going to end up getting all the same numbers. So you can start however you want to.
We'll still end up with the same.
You end up with the same answer, and that's why there's not a single right way to do this. There's a single correct answer, but no matter how we started, if we broke it up, we still get 1 3, 4 2s, and a 67.
Okay.
And that's the beauty of this. You can't start it wrong. Well, you can, but that's only if you divide wrong. Like if I said, oh, this is divisible by 5 or something.
Okay, I have a question because I remember the long division, but it's like when you're doing it, I get confused.
Okay.
It's almost like you're going really fast.
I am actually. So here's how I do short division, and I'm able to do it in my head. Okay, 6 won't go into 3.
Mm-hmm.
6 goes into 35 times, correct?
Mm-hmm.
Which is, or 32, so that's 30, and then there's 2 left.
Okay.
So 6 goes into 21 3 times, which is 18,
Okay.
and 21 minus 18 is 3. So I put that right there, and I get 36.
And it's 6.
And then 6 goes into 36 6 times.
Okay.
So that's
Now
what
I get it because I can actually see the numbers.
Yeah.
How
So
you're
the
doing
same
it.
thing, like here, 2 goes into 5 twice, with 1 left over, so 13, which gives me 6, which is 12, so you have 1 left over, which is 16. So that goes into 8.
Okay.
Better? So that's short division. Doesn't work real well with big numbers as your divisors, but with little numbers as your divisors, the short division can go pretty quickly. We have one more to divide. 615. What will that divide by? 5. Or I was told to do 3.
Or 10.
No,
Has
10
to
is
be
0.
0. Yeah, sorry, 5.
Okay, how many times will 5 go to 61?
12.
And into 15?
3.
123 will divide by 3. Yeah, because when I add it together, I get a 6. So 3 goes into 12 4 times. And then 3 goes into 3 1 time. And then 41 is
Should be
5. Should be.
No.
I don't think so.
Okay, there's a couple ways that we can do this, finding the greatest common divisor. But first of all, some of you may be more familiar with greatest common factor.
Yep.
Okay, so they're interchangeable because a divisor and a factor are the same thing. So you can have a GCF or the GCD. So whichever one you see means the same thing. Okay. We have glare, sorry. We write the prime factorization of each number. So you do a factor tree.
I was right this.
You can. You select each prime number with the smallest exponent that is common to each of the prime factorizations, and then you form the product of the numbers from step 2, and that will give you the greatest common divisor. I'm going to show you this, and so it might be more beneficial rather than writing this down to just see it in action. And then if you want me to pull this back up, I will. If you don't have any common factors, so the only factor you have in common is 1, you're called relatively prime. You're not prime, but you're prime to each other. Does that make sense? What? Did I do? Okay, anyway. So, not prime, but prime when you compare to each other. Okay, so I'm going to do 216 and 234. Okay, so the first thing I do is I'm going to factor each of them. Okay, 216 divided by 2 is even. 108, which will then divide by 2, which divides by 2, whoops, 27, which divides by 3, and then I get 3s. Okay. So I have 1, 2, 3 2s, and 1, 2, 3 3s. That's 216. 234 is even. 117 will divide by 3 because 7 and 1 and 1 makes 9. 3 goes into 11 3 times with 2 left over. With a 7, so 39, which is 3 times 13. Okay, so 234, while a larger number has less factors. Go figure. Okay, now, from what I had just shown you was the way the book has you do it, and they have you write down all the prime factorization and the exponents and everything, and then compare it that way. I think that's taking extra steps. Here's what I do. I look at everything they have in common, and I pair them up. They have a pair of 2s in common.
And there's 2 pairs of 3s in common.
They have a pair of 3s in common, and then another pair of 3s in common. Okay, those are the numbers that they have in common, and I ignore everything else. What they have in common is a 2, a 3, and another 3. I only write them down one time each, with one number for each pair.
Okay, so how come you, if they have,
Here's my first 2, here's my 3, and here's my 3.
so if you write it down, if you already did the pair part, can you just do the 2 times the 3 squared?
You can do 2 times 3 squared. Yeah.
Okay.
Either way, you'll get 2 times 3 is 6 times 3 is 18, or 2 times 9 is 18. This is the greatest common factor. You don't have to write out the whole list of the prime factorization here, and the whole list of the prime factorization here, and then the exponents and all that stuff that they were saying. Once you find the pairs, each pair gives you 1. Multiply those together, and that's your greatest common factor. This is the largest number that will divide into both of those evenly.
Oh.
Okay, 5 goes into 22 4 times, and 25 5 times, which will divide by 5, and then I get 2 3s. 5 goes into 8 once, it goes into 32 6 times, and it goes into 25 5 times. 5 goes into 16 3 times, and then 15 3 times, and 33 is 3 times 11. And then I come over and I change colors, and I have a 5 in common. So 2 5s. Oops. Okay. Well, whatever. And a 3. 25 times 3 gives me 75. Big, nice, spray painted, graffiti looking 75. Okay. 72. Yeah, it'll divide by both.
And then 6 and 6. And then 3 and 2.
Or 3 and 2. It doesn't matter what order you write them in.
And then 120, 10, 75.
Okay, now these are kind of branchier, but we can still.
I have a 6 in common.
We don't count the 6s. We only count the stuff at the very, very end of the branches.
Oh,
Now, granted, they do have a 6 in common, but we don't want to confuse that and multiply things back in, because if I use these 2 and this 3 and this 2 and this 3, and then also the 6s, I'm going to get too big of a number.
so only things at the end of the
Only at the ends of the branch. So I have this 3 can go with this 3.
and 2.
This 2 can go with that 2. This 2 can go with this 2. And that 2 can go with that 2.
Okay.
And then here I have a 3 left, and here I have a 5 left. So I have 1, 2, 3 2s, and a 3. So 8 times 3. Why don't you guys try that one?
Oh, never mind. We're trying that.
Yeah, try the last one.